Welcome to Networks Professionals.
Okay, let's dive right into this explainer and untangle the physical cables that secretly hold our entire digital world together. We often think of the internet as this invisible, magical cloud, right? But underneath the whole shebang, it's incredibly physical, and it's bound by some fascinating, really strict rules. Now think about the sheer scale of this puzzle. We have billions of machines globally that need a strict physical way to know exactly who is speaking and who is listening. Without a physical traffic control system dictating how these pulses of data travel down a wire, well, none of our emails, streams, or downloads would ever reach their destination intact. It'd just be a total mess. Let's kick things off with Section 1, the rules of copper, specifically cable wiring standards. Let's start with the baseline of how we connect things using classic copper wiring. The crucial point here is that physical copper cables rely entirely on two rigid pinout standards to organize the transmit and receive signals. We call them T568A and T568B. Inside that basic network cable you've probably plugged into your computer 100 times, there are these tiny color-coded wires. These standards dictate exactly which color wire goes to which specific pin on the connector, making absolutely sure the electrical data flows exactly where the receiving device expects it to. And this brilliantly illustrates our first major rule of cabling. On one side, we have straight-through cables, sometimes called patch cables. These use the exact same standard on both ends, so T568A on both sides or T568B on both sides. Pretty straightforward. But on the other side, we have crossover cables, which intentionally mix them up, using T568A on one end and T568B on the other. But why on earth do we need two different ways to wire the exact same cable? Moving right along to Section 2, the crossover puzzle, reversing TX and RX. Well, think of it like a human conversation at a loud party. If two identical devices both try to transmit, or TX, into the exact same wire at the exact same time, it's just chaotic noise. Neither device is actually listening. A crossover cable solves this by physically reversing the transmit and receive wire pairs inside the casing. By crossing the TX and RX pairs, the cable physically forces the transmit signal from the first machine to neatly land on the receive pin of the second machine. It literally turns two machines shouting at each other into a polite, functional conversation. There's a really simple logic to applying this, almost like a cheat sheet. When you connect dissimilar devices, like, say, a PC to a switch, you use a straight-through cable. Why? Because the manufacturers already designed the switch to complement the PC. Their transmit and receive pins naturally align. But when you want to connect similar devices directly together, like a PC directly to another PC or a switch to a switch, they physically require a crossover cable to manually reverse those wire pairs. Otherwise, they just can't hear each other without a hub sitting in the middle managing all that traffic. Which brings us to Section 3, the fiber optic highway, speed of light. So what happens when we need to break the speed and distance limits of traditional copper? Okay, let's dive into this mind-boggling number. By ditching copper entirely and using light signals, fiber optic cables unlock a massive bandwidth of 60+ terabits per second. Instead of sending electrical pulses over metal, fiber shoots pulses of light. This completely changes the physical game, allowing a staggeringly higher volume of data to travel across the globe in the blink of an eye. Literally. And fiber doesn't just solve our speed problems, it absolutely destroys our distance problems, easily carrying data over 2 kilometers without losing the signal. You see, copper signals degrade relatively quickly the further they travel, but light can fly.
Now, what's really interesting here is the trade-off of upgrading to light. Because we're no longer using electricity, we gain total immunity to EMI, or electromagnetic interference. You could run a fiber optic cable right alongside heavy industrial machinery, and the data wouldn't be corrupted at all. We basically have two main flavors for this: single mode for those incredibly long distances, and multi-mode for slightly shorter runs. But here's the catch. We have to treat these delicate glass and plastic strands with incredible care because they're physically fragile compared to rugged copper. And just like we saw earlier with copper, we even use special crossover fiber patch cables to manually swap the transmitter and receiver connections between fiber transceivers. The medium changes to light, sure, but the fundamental need to align the talkers and the listeners, that remains exactly the same.
And now for my favorite part, Section 4, the Auto MDI X plot twist, adapting instantly. Just when you thought you had to memorize all those strict crossover rules, modern networking throws us a brilliant curveball. This built-in intelligence basically does the homework for you, automatically adapting to whatever cable you plug in. Modern networking devices increasingly use this amazing feature called Auto MDIX. If you accidentally plug a straight-through cable into two switches, which historically would have caused a total communication failure, Auto MDIX simply detects the cable type and electronically adjusts its own transmit and receive pins on the fly to fix your mistake. It essentially makes the traditional dedicated crossover cable a relic of the past for everyday users, a real game changer. As we wrap up this explainer, I'll leave you with this thought. As our network hardware gets smarter and our internal software continues to effortlessly override our physical connection limits, what will the cables of the future actually look like? Will the strict pinouts of today become completely invisible tomorrow? It is amazing to consider how far we've come from meticulously crossing tiny colored wires to having software instantly adapt reality for us. Thanks for joining me as we unraveled the physical layer today.
Thanks for watching.